you let me know when you're lost, yeah, because I cannot judge. So I'm having the model now open together with the map, and you see it's displayed in this mesh-like appearance, which is typical for X-ray maps. Used to be. Personally, there's different styles how now to use Isolde. My personal preference is changing to white background on the top here. And I like to look at it not with a mesh, but with a normal surface. And you can do this under Show Map Settings dialog, which is the lowest one here in the Isolde window. And then you click on the ice cube. So currently we are on this mesh representation. If you click on the ice cube, you will see it changes to this surface representation. And that to me is, whatever you prefer is better for you.
Can you do me a favor? Because I had some Zoom issues here. Yeah. Can you just tell me again how you connected the model with the map?
If you go to the very top on the top tab, Associate Real Space Map Model, there you click on Go, and then it will happen. What you see on your screen is that the map will disappear, but in the lower right corner, you see also the map color change from the standard default gray to blue. Mm. And if you now try to move the model, and I can do this with the middle mouse button, I don't know how this is with a Mac mouse if you only have two buttons, then it will reappear the scale bar. But you can also manually move the model under the right mouse tab in ChimeraX at the very top. And you can also say here, okay, I want to change, translate, rotate, and then the map should reappear. And then we can use it as before. Now it's connected, and you can change the threshold here. You can also change the step size if you want, but this is typically how you start off. And these are the first steps. Then let's go into Isolde a little bit and start there first. So this is the starting window essentially. So here we can change the appearance of the map. We can change the color. Whatever we like. We can have some weird surface view. It's not so useful. Now it's in black. You can change it back to the standard blue. So standard functionalities here. What we have down here is the so-called spotlight radius. And what the spotlight radius does, this is the radius in which you see the map. You can now see it's basically limited to this field of view. If I increase this, let's say to 50, I will see more of the map. And you will see that also the corresponding model in this area is now being displayed. If you have a very strong graphics card, that's no problem. If you have a weak graphics card, the more you display at the time, the less smooth things will run. So I typically work around 20. You don't need to display everything, but sometimes you just want to investigate the map. And then you could, for example, switch off the model, and you can just look at the map. And also at bigger scale. I changed this now to 50. I can see almost the entire map. And I can still use this here in the standard ChimeraX model viewer panel, where I can switch off and on basically the model, but I can also do this for the map. Okay, so I now will use just spotlight radius 20. Go inside, and this is one of the basic functionalities. So now in the new Isolde version, you can see these three options. This is very new, and if you change to quick, that will help you in running simulations on a computer that is having not such a strong graphics card. So if you want to have the best fidelity, then you go on high, which is default. But if you have, let's say, MacBook Air and you still want to try it, you probably want to switch to quick during the simulations to make it run a bit smoother. The rest here is basically not super important, except for the area up here. This is controlling the simulation in case we want to start it. And I will show you later what the difference is. So the simulation will always run on those residues that are being selected, and plus 3 residues to the left and 3 residues to the right of your selection. So if you select 10 residues, it will also mobilize the 3 residues to the left, N terminal and C terminal, and all the residues that are in range or in the distance of 5 Armstrongs. And of course, you can change this. The default is 3 and 5. And maybe another parameter that I'm not changing very often, only basically rarely, is the map weight. So you can, this is the default setting now, and it's just being judged by the quality of the map. So I provided a 2.1 Armstrong map, which is really good. So the map weight is relatively high. If you have a low resolution map and you load this, you will see that this value is not as strong. And it basically tells how much the map should pull on the model. So if you have a high resolution map, you have a lot of information. So the information in this map is basically determining more where the model is going. Whereas if you have a low resolution map, this weight is going to change, and you rely more on the geometry and prior knowledge of how the geometry of a model should look like. Meaning that if you have, for example, a helix at high resolution, 2 Armstrongs, we see basically all the side chains and how the helix looks like. And I think we can also make a case here. Trying to zoom in one of them. Here's one. We can basically see everything of this helix, right? So side chain density is amazing. So then, of course, the map weight is really high. But if we low pass filter this, and this is now the first command that I will type in here, you will see that things become a bit more challenging when the resolution drops. And one thing you may want to do during model building is you want to change B factors. And typically you can do this in rely on that the guy who's processing or the girl that is processing the maps provides you with maps sharpened with different B factors. But you can also do this in Isolde very quickly, and you may want to do this anyway. And the way how to do this is you say, I need to check myself. That's one of these commands I typically have in my mind, but now, of course, I cannot recall them. So I sent you this file where I also have all these commands listed. Here I have it. No, sorry. Okay. The command is volume space Gaussian space hashtag, and then you provide the ID of the map, and you write space B factor space, and you provide a number. In this case, for example, I say now 200. So volume space Gaussian space hashtag ID space B factor space, and then I chose 200. And this will apply a B factor of plus 200 to this very map. If I press enter, it will start calculating. And what you see is a new map, which is now smoothened by a B factor of plus 200. And you will see already that the sidechain information is basically gone, but we still see a helical tube. And once you've done this, you can basically go again to the existing volume tab, and you will see now that this Gaussian map appears here as a new map. So I can click on this, I can say go, and it will also be connected to Isolde. And you now see that the weight changed, right? Because now we have a low resolution map. Now everything is more dependent on geometry than on the map. So now I have down here 2 maps, and I can switch between them. So whenever I want to use the high resolution features for model building, I use the high resolution map with the appropriate B factor. And if I want to see areas, for example, loops at the outside, which at a certain sharpening factor may disappear. We see this, for example, here at the periphery, that the density smears out with a given B factor. So I can either change threshold, in this case that is sufficient to bring it back. But I could also, in cases where this is not happening, I could change to a different map and try to see whether when I have a map that is low pass filtered, whether it comes back, and then it would look like this. Sometimes it helps to trace basically the main chain, in case the high B factor that was applied is too high, and it basically distorts the map. And this happens quite a lot, especially in the periphery. So when I start using Isolde, the first thing I do is I hope I can get a map which has a very moderate B factor, and be aware that when you get something auto-processed from Reliant, it typically uses a very, very high negative B factor, sometimes in the 160s or so. So you can supply your own value to this. Sometimes it's good to have a very moderate B factor, which is only 10, 20, 30 or so, or minus 60. And then you can, in Isolde, can supply your own B factor on top of it. And then I make 2-3 maps to the one that I'm having, which are with higher B factors and with lower B factors. And I can use them all for the model building. Sometimes I want to have more details. Sometimes I want to have less details there, but the gross features, the secondary structure elements. Okay, but for this session now, I will only use the high resolution map. So I can just switch it off here and it's gone. And I just use this map. Okay, next tab is basically the rebuild functionality up here and the validate functionality. And the first thing I wanted to do is I go to the validate tab first, because that is what Isolde initially has been designed for. It's a refinement program. So you can use it to assess model quality. And one of the things, or there's basically, I would say, 3 main features, and they're listed here it's 4, but I think the 3 main ones that you will also see in, let's say, validation metrics when it comes, for example, to model property validation, or after refinement programs, whether you use RefMac, Phoenix, Rosetta. In the end, you do a validation and they will assess different parameters of your model. The first one is the Ramachandran plot. And if you click here on the Ramachandran plot show, you will see that it pops up for this very model. And for those of you who have never seen it, it kind of gives you an idea whether the backbone geometry of a residue is okay. So it's okay means that that the angles, psi and phi angles of this backbone for a given residue are in agreement with what has been seen essentially in high resolution structures. So this is where all this is basically originating from, that people have used, very experienced model building experts, I would say, have used 8,000 high resolution crystal structures in the 1 Armstrong realm, and have modeled them and used those information to basically define what are these angles. How can these angles look like for certain residues in these high resolution structures? And from there we have libraries, and these libraries are basically in the back here of Isolde. And whatever is within this green, within these yellow areas is basically a backbone configuration for a given residue that is favored. And you will see that the dot appears in green. So we have this here and down here, and other spots are here. And if you are within this purple area, they are allowed, so to speak. And you can have, typically structures have 2% of their residues that are in the allowed area, statistically. And if they are outside, they will appear here, somewhere in between, and they will be red. So this structure is a 2.1 Armstrong resolution structure, so the model is very good. So we don't have any outliers, backbone outliers, but we will generate some in a minute. So this is the first assessment. So backbone geometry is really good, but this is for general amino acids. So we have some special ones. Most interestingly, probably proline, and you can change the graph according to these. So now I can change to isoleucine and valine only. I can change to residues that are preceding proline. Glycine residues are a bit different because glycine has no side chain. Transproline residues, and you see here already there are a few that are only in the allowed but not in the favored region, so not in the yellow areas but in the one in the purple area basically. And cisprolines. So since trans-proline residues here are a bit special, you can actually go onto one of these dots and you will see where these residues appear. So there's actually 4 of them. And this is because it's a tetramer. And you find them at position 188 in all of the 4 chains. So if you click on them, you will be sent to this position and it will be centered. And now you see this position and you can investigate a little bit. The first thing, and this is what it tells you here, is basically the orange color of this C alpha. It tells you here that the backbone geometry is not in the favored area of the Ramachandran plot, whereas the neighbors are fine. This is just a basic investigation now. So this is one of them, of these metrics that we are looking for. And ideally, you want to have as many residues as possible in the favored region. And I think this has been done very well here in this structure. One must say, though, that you always need to make a compromise by model building. So if you have a high resolution map, such as it is the case here, the way you should model is according to what the map tells you. And if the map tells you that this is an outlier and has a bad backbone geometry, then this is what it is. So the goal is not to make beautiful stats, but the best possible model according to the map that you have. But if the map is weak, we rely more and more on prior information and what we know about model geometry. And then you try to focus on making a good geometry, because if you cannot provide experimental data to validate, let's say, an outlier, then it doesn't make sense to actually model it because you don't know any better. And I will give you an example now for Rotamers where this is the case. Which brings me to the second tab here. So we can hide the Ramachandran plot and we can go to Rotamers directly. And if you open this, you will see a list of Rotamer outliers. And if you click on the first one, again, you will be sent to this position in the structure. And you see this now with this mark that this glutamic acid is an outlier, which means that the configuration of the sidechain with these angles is highly unlikely, and it has basically is not being seen in the high resolution structures. So you should think about taking care of this. On top of this, and what you can see here is that this position is at the very outside of the structure. If I blow up the map, there is some sidechain coming up, density here, but I don't see the entire sidechain. This has, especially in cryo-EM maps, 2 reasons. Reason number 1 is, and this would be the same for X-ray maps, whatever is located at the outside and has a long sidechain can move a lot. And if something can move a lot, there is no fixed position of it, and then you rarely gets nice sidechain density. The second point, and this is more particular for cryo-EM maps, is that the first residues that suffer in the electron beam are the ones that are negatively charged, and this is the case for glutamic acid. So if you have radiation damage, so to speak, it will first destroy the density that belongs to negatively charged residues. In this case here, it could eventually be a combination, but most likely we don't have any density here because it's located at the outside and it has just a lot of flexibility. Nevertheless, if you see such a density, there is no reason to model it as a Rotamer outlier because this outlier is not covered by the density neither. So I would change this residue to a Rotamer, which is in agreement with the library of glutamic acids. Rotamer positions, and we will do this in a minute. So this is still basic investigation. You will see that the backbone geometry in this area, however, is very beautiful, and all the other residues also look very good. And like this, you can basically work yourself through the list. The top ones here are the most dramatic outliers for the Rotamers, and if you go down the lists, you see here p-value approaches 2%. Here we have a lysine residue. You see that this color of this mark here changes to a yellow, so it's not as dramatic as the big red one. Here it's the same, it's a lysine residue. It's pointing out to the surface, to the exterior. And it's typically the case in proteins because you need some charged residues on the outside to make it soluble. but because it can move a lot and has a lot of different sidechain conformations that are possible, we hardly see the sidechain itself. Again, doesn't make sense then to model it as an outlier because it's not covered by density. Whether one wants to be so pedantic to change it, okay, maybe that's more than something I would do, but this is just one example. So these are rotamers. Coming to the last point, these are clashes. So in these structures, there are no clashes. And why is this the case? This is the case because they did a good refinement job. A clash is essentially if two residues come into too close contact. I think it's rather obvious that two atoms cannot be located in the very same position in 3D space. If they come, however, too close, and all the validation programs use different metrics for this, they are reported as clashes. In Isolde, that is not a big deal because Isolde is using a minimizer function. The moment you start a simulation, what Isolde tries to do is trying to provide enough space between all the residues. In fact, if you have a major clash, that is, two residues occupy the same position, Isolde sometimes has issues to start because it cannot deal with this. However, if you're using other software tools, such as Qt, you can easily model two residues in the very same location in space and generate a massive clash. In such cases, you would basically end up with a list here with the atoms that are actually clashing and the overlap of these atoms. And these are the three metrics I wanted to basically show you, which we can fix when we're dealing with Isolde and when we do model building. So, as I just noticed here, for example, if you just investigate, and this is another observation, you can clearly see that this arginine sidechain is not where it is supposed to be sitting. It's outside of its density, while it's not flagged by any of the metrics that are used here currently, because the backbone geometry is okay. And also the sidechain is favored Rotamer. So it's not flagged, but it's still not correct because it's outside of its density. And if I investigate the environment, I think it should probably make a contact with this glutamine residue and eventually also with the backbone here. And for this, maybe Thomas can give a little introduction into z-scores at some point, where we also try to make use of fit of the model into the density. But this is something, if you model something yourself, you should basically, this should not occur to you because you're going through residue by residue, once at a time. Same thing is here. I think also this residue is modeled in the wrong rotamer. You can see basically that it should run more like this. Anyways, coming to what I prepared for you today to get a first start on Isolde, running the first simulation also on weak computers. So what I would like to do now is for you to basically move around a little bit in the model. And the way you can do this, other than like randomly scouting for positions, which is a very good start, but you can also be more specific. You can basically center on any residue that you want to. And you do this with center view. So it's cview as a command, cview, and then you type space, and then a slash, and you provide the chain where you want to go. In this case, I just chose A, double dot, and then you provide the residue number. And in this case, I would like to send you to 295 in chain A. And if you do this, you will enter up at this residue, and it will be centered around, and you will find that you see a tryptophan residue. And you don't have to be a magician to see that this can't be. Personally, for me as a model builder, I cannot stand this to see such nice density, which we rarely have, and you see how wrongly it is modeled. Another thing where probably z-scores could be very beneficial. You see that the backbone geometry is just fine. It's a green dot here. You don't see any marks for an outlier of the sidechain. But obviously, the sidechain is in the wrong position. So how can we now actually fix this with Isolde? So first thing you can do is, and what you need to do is, you need to use your control button on the keyboard and your left mouse. And if you click control and the left mouse, you can actually select the C alpha. And it should then light up in green. Like this, you can basically select whatever you want in the model. But this selection is now being used for Isolde to tell it, to inform Isolde what should be simulated in the structure. So you can simulate the entire molecule at once, or you can do a simulation locally. If you have, I always recommend to do it locally. And if you have a weak computer, simulation of the entire molecule will anyway be not really feasible. So I select now the C alpha of this tryptophan, and to now fix this, we can actually start a simulation first. For this, we go into the simulation tab on the very left. And what I will do now first is I will change the temperature, which can be done here. So if this is 20 kelvins now, this is the new default. You can use 100, you can use 1. It basically means it heats up the temperature of the simulation. So the hotter, the more things will be moving. The lower, the less they will be moving. So I will start now with 1. And what I will also do is I use the defaults here. So it's 3 residues to the left of this selection and to the right, plus the environment of 5 Armstrongs will be mobilized. If I now start clicking play, the first thing that will appear is an error. And this is because the force field that needs to be generated to run this ND simulation depends on hydrogen atoms. And typically the hydrogen atoms are not in the structure, so you have to bring them back.
Bringing back the hydrogen atoms into your structure is needed because the MD force field is actually trying to accurately model the physics of the molecule. And to be able to do this, the molecule must contain everything, including these hydrogen atoms.
So by clicking OK, you will be asked automatically to add these hydrogens. And you say, OK, this will take a second depending on your computer speed and on the size of the model, obviously. And once this is done, you will see that here in the log file that these hydrogens have been added. And with this, we can basically control-click again on the tryptophan and now start the simulation. Again, I'm having 3 residues mobilized, 5 Armstrong environment, and 1 Kelvin, so things won't be moving much. And now I click on play, and what is happening, the simulation will start. And you will see that things start moving. And they don't move a lot because I'm at 1 Kelvin. But if I change this to 100 Kelvin, you will see that things are basically wobbling like mad. So like this, you can basically change the temperature you want to work with. Personally, I prefer working at lower temperatures, which gives me the feeling of having better control. So I would reduce it now to 10, which is typically what I'm working with. So things aren't moving that much, but you can even go lower than that. So down here now, you will see that 3 new buttons appeared. So we have this green racing flag, the red one, and the green stop sign, the red stop sign, and the red stop sign with the racing flag. You always have this little information that comes along when hovering over the button. So what these flags mean is if you press on it, it will save a check mark. That means whatever I do will be saved. So I can now left click, for example, on this main chain, and I can actually start moving it around wherever I want. And you can see that whatever I do, I will manipulate the model. Sometimes the backbone conformation will go into a red dot, then I can move it back, it will be good. If I go into the other direction, you see that now the backbone is okay, but the Rotamer is actually not fine, things like that. If I have applied a change and I click on the green flag, this is the coordinates that will be saved in Isolde. And whenever you want to return to your starting coordinates, it will return to this checkpoint. So if you introduce the big mistake and you generate a checkpoint, you cannot go back to the original starting coordinates. If you, for example, I now do something like this, now I generated a even bigger arrow, and I generate now a checkpoint because I think I'm satisfied with this. So now I have generated it. I want to change something again. Now it looks better maybe. And I go on this one here, which says return to the last saved checkpoint, and I do, and I will end up in the situation that I saved, which is not good, but this is just a functionality. When I click on green stop, it will stop the simulation and it will save the current coordinate file.
Clicking on the big red emergency stop button instead discards everything from the simulation, resetting things to exactly how they were when you press the play button.
And you can also stop and revert to the last saved checkpoint. So I think these are basically, if you use checkpoints a lot, you don't really see a difference between using those. Anyways, so what I wanted to aim for now is to basically use some of the functionalities of Isolde. So how can we fix this actually? So I think one of the obvious things is that the sidechain is in the wrong position. So, and I want to address this one first. How can we do this? So if you control click on the backbone, so you only have the tryptophan basically selected, you can go into the rebuild tab. And in the rebuild tab, you see all these functions. And the function here, the top ones are about changing the backbone conformation, which is what I'm not interested in right now. But I want to change the rotamers. And these are basically those options here. And if you click on these ones, on these arrows, you will see that the software will cycle through different rotamer options. And the one that is the one currently is the one that is represented in thick. And the one that it suggests is the one that is displayed next to it. And you can cycle through all the rotamer options that are basically there until you eventually find one that is satisfying. And you will soon enough see there is none that is basically satisfying. This is one way of doing it. Here are other ways how to do this. And maybe we go through them next time, because what I think is the most intuitive thing to do is you can just click on one of the atoms that you want to move into a different position, and you click it just with the left mouse. And when you do this, you can actually tuck the whole sidechain. And that's what I'm doing now. I'm just tugging it into its position. And I think everyone can agree that the fit here is now much, much better. Also, the backbone has been fixed, so both of them are green. And what appears here is a clear rotamer outlier, indicated by this red sign. And this is the perfect example. That wasn't actually, that was coincidence that this happened. This is a perfect example where the map tells you that this sidechain configuration is correct, although the model validation tells you that this is an outlier. But this outlier is clearly supported by the electron density map or by the EM map, and therefore this is the right way to model this tryptophan. And it was wrong in the model before. And yes, if we now go to the valid, we can now stop the simulation here with the green stop, and it will save this new coordinate file. And if we now return to the validation tab, and we go to rotamers, we show the rotamer tab, you will see there is a tryptophan in a rotamer configuration, which is highly unlikely. However, in this case, it's the correct way to do. Now we have basically fixed one of the problems, so to speak, in the map, in the model, and it's a better model now. And you can also see you can also see from the environment why this is the right rotamer. And this is, if you have a lower resolution map, you may rely more on the environment. So in the neighborhood, you have this proline. So this is a hydrophobic packing interaction, which is satisfied now. It was satisfied before. But what is new here now is this hydrogen bond that can only form now between those. And you can actually display hydrogen bonds if you type H bonds as a command. Somehow this misdisplayed here for whatever reason. Maybe one has to, I don't know why it's doing this now. Seems to be a bug. So if we were, it's kind of not going to the oxygen here, which it should. So the hydrogen bond is formed between those two. So that also would support placing it as an outlier, even if the map quality wouldn't be as good. If you want to running a simulation with hydrogen bonds on is a disaster. So we need to turn them off again. And you can also do this up here in the tabs. If you cycle through them, I always have to look for them. H bonds, hide H bonds, and they're gone again. So now we have basically fixed this. And I would like to come to the last part for today, which is, can we build also some residues newly in Isolde? And for this, I would like to move on in the structure to other positions. And of course, I did this to the model. This is why you have a version that was generated by me. So to make things a bit easier, I first would like to get rid of the waters. So what you see here at position 402 is a water molecule. The map is so good that you can actually start seeing the hydration shell of the protein. So you can start modeling waters. In Isolde, what you can do, or in general, it's a ChimeraX command, is you can select. So this is the shortcut is SEL for select. Then you do a tilde, which on my keyboard is shift click, and then on the top left under escape. This is, however, Mac function. I don't know whether you can find a tilde on yours. And then we type protein. And that would select everything that is not a protein. And this can sometimes be a bit confusing because it's now also selecting the map, and that makes it difficult to see this because the map is also not protein. But you see now when I disable the map, it only selected all the water molecules. And if there are other components like lipids or a DNA or some inhibitors or something inside, they would also be selected. And if we now say delete, DEL, space, cell for selection, and press enter, it will delete all these elements. So all the waters are gone at once. If you use this command and you have a DNA inside, the DNA would also be gone. But I wanted to do this to make it a bit easier. So to navigate to the position that I manipulated for building is right next to this tryptophan. If you are lost in your map now, you can just go to the position 296. So if you say center view /A /296, you will be sent to this position, and what you will see is there is empty density. So the model ends here, but the density continues. And you can basically follow, I don't know, I hope you can too. You can basically see that the main chain continues like this. Can you see my mouse? Maybe I can use a pointer next time. So the main chain continues up here. There is a side chain sticking out, and we can basically follow the main chain. I just deleted a couple of residues. The main chain continues further. Here's a bulky residue with the side chain, probably a phenylalanine. And then the main chain continues up here. And I deleted 7, 8 residues. Here's another side chain, tyrosine. You start seeing the hole in the residue, and there's something attached to it. So there's a hydroxy group at the end. And like this, I deleted a couple of residues for you to do rebuilding. Okay. The way the model or ChimeraX depicts a disconnected chain is basically this dashed line. And it's a straight line between the C terminus and the N terminus. So here you see the N terminus, which is position 306. So if I go 306, you see this is where the N terminus is. And you see this pseudobond, which is a dashed line. And will be a straight line to where the C terminus is, which in our case is 296. So if I go there, you see the other end. And in between is what is missing. Since this is 10 residues in total, you can also give a range, center view from 296 to 306. You will see the entire piece that is basically missing. So we have to model nine residues in there. How to do this? So in Isolde, there is now a new functionality for adding residues, which I haven't tested myself. So one way of doing this, I will try briefly whether it works. Isolde add ala. Okay, that's not the command. Would have been too easy. Okay, then we do it the old-fashioned way. Maybe you will encounter this problem anyway sooner or later. So what is very cool about ChimeraX and Isolde in general, if you are as capable as Lux or Thomas or whoever else is in scripting, Maurice, for example, you can use basically the a shell within ChimeraX. So then you find this under Tools, General, Shell, and if you click on it, it will open a shell for you. Yes?
I think you just had to add, you just have to add Isolde add AA ALA, so amino acid ALA, to work the new way.
A, like this?
AA, double A. And then the residue name, yes.
Gives me, if stem residue is not specified.
You have to select the residue, the last residue, where you want to add it afterwards. So it adds automatically at the C terminus.
Okay, let's try. Select A 296. No, okay.
Try to put ALAs in small. Okay, then I don't know. I played a bit with it a week ago or so, 2 weeks.
Yeah, but there's such a command in Isolde now, and I will dig it out for next time. But there, I think for now, I also wanted to show you the shell because it's going to be important for some of the other commands which are not yet in Isolde. So if you go to Tools, General, Shell, you get the shell, and you can actually incorporate it here into ChimeraX, and you can use it to enter commands. And one of them is actually adding residues. So if you go into the file that I sent around, now I need to briefly find the one that I have. This one, you find a list of commands. And one of them, for example, is adding residues to the N terminus and adding residues to the C terminus. So what you can basically do is copy all of this. And I know it's a little bit not so straightforward, and the add command will do the same job next time we do this, and you can just copy paste it here. What you need to do now, however, and this is quite important, is you need to really select the C terminus only, and you do this with Control, clicking on the C terminus, not selecting the whole residue, just the C terminus. And you need to define here that you actually want to add an alanine. And if you do this and press Enter, I hope something is happening. Or maybe my Isolde crashed. Okay. Okay, I don't know. Maybe, I don't know why it's not working. Okay, then we skip this for the next part and I figure out the Isolde add command. So I briefly try to basically use Isolde add residue. See whether we can figure it out. Probably not now. Okay. Yes. So maybe one last try here. Why did it have now synchrone? Now it's working. I don't know why. You saw that? Now I have an alanine. I don't know why it wasn't working before. So now I generated with this command an alanine, which is now the new C terminus. So I started from 297, and now it added actually 2. So it worked twice. So the residue that we changed the Rotamer was this tryptophan. The new C terminus that I had generated was this alanine, and now like this, with using this command iteratively, I added 2 more alanines. And of course, these are not alanines, which you can see from the side chain. And if you now click on them, like one of them and you start a brief simulation in this area, and you can now basically change also the residues that need to be mobilized. It can be very, very local, and you don't need to change the environment so much. So you can really go only in this area and you start a local simulation. Then what should happen is it starts moving already pretty well into its density. And you can see with the thin lines that now these residues in the environment are not being mobilized. It's just this part here. So if I increase what I want to see in the environment and I do the same, you will see that also the environment is moving. So for building purposes, to first get it into its correct space, I tend to not mobilize the environment at all. Okay. And then one last thing that I would like to show now, and you can either, of course, type already the correct residue here, which is, of course, the smartest way to do, but you can also change residues on the fly. And this is swap AA, I guess. Yes. So the command is here, swap AA for swap amino acid. And then mouse mode, swap AA space mouse mode, hashtag for the model ID. In this case, it's 1 or 1.2 to be more specific. Then we want to look at the chain. Chain is A, residue position is 297, and we want to change this residue into something else. And into what? This, if you are good enough to see this from the density, we can do it like this. But this is what I provided also in my email, the sequence file for, because in the sequence file, you can basically now look at the sequence and see what you expect in position 297 and choose this residue. From what I would say, it's probably valine. Maybe I'm wrong. But if you type valine here and click enter, you can basically choose the side chains that you want to try. But with the sequence, it's leucine, fits very well. You can change it to leucine. This one here probably is an alanine. Yes. And the next one down the row, I don't know what it is. So I would have to check the sequence myself. So for doing this, you can go to the UniProt webpage, use the identifier that I gave you. And with this, I think we can close for today, and you can start trying to build the rest